Some of the universe's earliest galaxies appear to have grown up faster than anyone expected. That is the surprise. When astronomers point powerful infrared telescopes deep into space, they are also looking back in time. The farther the light has travelled, the younger the universe was when that light began its journey. For decades, the basic picture was simple. After the Big Bang, the universe cooled. The first stars ignited. Small clumps of matter began pulling together. Over time, those clumps became galaxies like the Milky Way. But recent observations have revealed galaxies from very early cosmic history that look unexpectedly bright, active, or mature for their age. Not all of them are fully confirmed in the same way, and scientists are careful about that. Some may turn out to be closer, smaller, or less massive than they first appeared. Still, the pattern is fascinating. The young universe may have been better at building stars feeding black holes or gathering gas than many models predicted. Imagine finding a city skyline where you expected only campfires. That does not mean the whole story of the universe is wrong. It means one chapter may have moved faster or worked differently than we realized. The single-sentence takeaway is this: the early universe was not empty, slow, or simple. It was already busy. Why does that matter? Because galaxies are the cosmic homes where stars, planets, chemistry, and eventually life can exist. Learning when galaxies first became organized tells us how quickly the universe became capable of complexity. The mystery is not that galaxies exist. The mystery is how quickly some of them seem to have assembled. And that leads to the next question. When astronomers say a galaxy is early, how do they actually know? The answer begins with light stretched by the expansion of space itself. A galaxy can be ancient, not because it is far away in ordinary terms, but because its light is old. Light does not arrive instantly from deep space. It crosses the universe for millions or billions of years. So, when a telescope catches that light, it is receiving a message from the past. For the most distant galaxies, that message has also been stretched. Space itself has expanded while the light was traveling. What began as visible or ultraviolet light can arrive as infrared light. Astronomers call this redshift. Redshift is one of the main clues used to estimate how far back in cosmic history a galaxy belongs. But there are levels of confidence. Sometimes scientists estimate a galaxy's distance from its colors across different filters. That can identify promising early candidates, especially when a galaxy seems to vanish in shorter wavelengths and appear in infrared. But color alone can be misleading. Dust, unusual stars, or a closer object can sometimes imitate the signal. A stronger test is spectroscopy. Instead of measuring broad colors, astronomers spread the light into its components and search for specific fingerprints from atoms and gas. If those fingerprints are shifted by the same amount, the distance estimate becomes much more secure. This is why careful astronomy often sounds cautious. A headline may say one of the earliest galaxies ever seen, but the scientific question is, how was it measured and how certain is that measurement? What is known is powerful. Telescopes are finding real populations of galaxies from the universe's youth. Some are forming stars rapidly. Some may host growing black holes. Some appear brighter than expected. What remains uncertain is exactly how massive they are, how common they are, and whether our models of early star formation need small adjustments or deeper changes. The wonder is that light itself becomes a time machine. It carries distance age, chemistry, and motion across the darkness. And once astronomers trust that message, a bigger question appears. How did the first galaxies grow so quickly? How did the first galaxies grow so quickly in a universe that was still young? That question sits at the edge of modern astronomy. A galaxy is not just a cloud of stars. It is a living system of gas dust, gravity, newborn suns, dying stars, and often a central black hole. In the early universe, the raw ingredients were simpler than they are today. There was mostly hydrogen and helium, with only tiny amounts of heavier elements made later inside stars. Yet somehow, gravity began turning those simple ingredients into structure. One possibility is that dark matter helped build the scaffolding. Dark matter does not shine, but its gravity can pull ordinary gas into dense regions. Those regions can collapse, cool, and ignite waves of star formation. Another possibility is that the first galaxies were unusually efficient. Gas may have fallen inward quickly. Stars may have formed in intense bursts. Black holes may have grown early and added extra light, making some galaxies appear brighter than their stars alone would suggest. None of these ideas has to replace the Big Bang. The question is not whether the universe began hot and dense. The question is how fast matter organized itself after that beginning. This matters because the first galaxies changed the universe around them. Their stars flooded space with light. Their explosions spread heavier elements. Their radiation helped transform the foggy early cosmos into a more transparent one. What scientists know is that the early universe was active. What they are still testing is the pace, the recipe, and the variety of that activity. The memorable takeaway is simple. The first galaxies were not just ancient objects. They were engines of cosmic change. Every starry sky we see today is connected to that beginning. Our galaxy, our sun, and the atoms in our bodies all belong to the same long story of matter, learning how to shine. And the deeper we listen to ancient light, the closer we get to the universe's first chapter.